Welcome to this explainer. Today, we are going on a seriously fascinating journey. We're going to follow a physiological signal, a literal human heartbeat, from the exact moment it pulses inside a body, all the way through a modern, ultra-smart portable health monitor until it finally pops up as life-saving data on a screen. We're diving deep into the design of a portable ECG and blood oxygen monitoring system built around this incredibly cool piece of tech called the AFE4400. If you've ever found yourself wondering how your smartwatch or a clinical monitor actually takes the physical language of your body and translates it into digital insights, well, you are in exactly the right place. Let's get into it. Okay, let's look at our roadmap for today. First, anatomy of the hardware. Second, processing the vital signals. Third, measuring heart rate and SpO₂. Fourth, the mobile app experience. And finally, number 5, the future of telemedicine. Section 1, anatomy of the hardware, building the foundation. So, before the software can do its magic, we have to talk about the physical hardware where this whole process starts. At the absolute core of the system sits the Texas Instruments AFE4400. You can really think of this component as a highly skilled lightning-fast translator. Because, your body doesn't speak in ones and zeros, right? It speaks in microscopic electrical impulses and subtle shifts in how light is absorbed when blood pumps through your veins. So the AFE4400 is an integrated analog front end. Its entire job in life is to sit right on that boundary between the physical world and the digital world. It captures those optical pulses and translates that complex human body language into a clean, digital language the rest of the computer can actually understand. But, of course, it doesn't work alone. It's backed up by a completely custom-printed circuit board, or PCB, designed in Altium Designer. And a massive detail here is the strict analog-digital isolation. That's absolutely crucial because digital components can be super noisy electrically, and we definitely do not want that noise messing up the delicate analog signals coming from the body. To make the whole thing smart and wireless, it integrates Bluetooth low-energy microcontrollers, using chips like the ESP32 and NRF52. And powering the whole shebang is a solid 7-volt lithium-polymer battery kept perfectly stable by a low-dropout linear regulator. Now, what's really interesting about this slide is this single number right here, less than 30 milliamps. That is the ultra-low power consumption of this system while it's in active mode. Because of the highly optimized firmware and the AFE4400's smart sleep modes, this device practically just sips power. And that's a total game changer. It means this isn't just a quick spot check tool. It's a continuous, mobile monitoring solution that a patient can wear for hours and hours without stressing over a charger. Section 2, processing the vital signals, filtering the noise. Capturing the signal is honestly just step 1. Now we have to refine those raw microvolts into actual medical data. This table really shows off the technical chops of the system once that signal is processed. Look at these benchmarks. It accurately tracks heart rates all the way from 30 up to 200 beats per minute. It measures blood oxygen saturation right in that critical clinical pocket of 85% to 100%. And it captures tiny ECG amplitudes from just 0.15 to 5 millivolts. These aren't just random stats. This proves the clinical viability of what we're capturing. But to get the data this crisp, the system has to do some serious heavy lifting. And that heavy lifting is all about filtering. See, the human body is constantly moving, right? We generate baseline wander, muscle noise, electromagnetic interference. It's a mess. To fix this, the system uses active bandpass filters, tuned exactly between 0.5 and 40 Hz for the ECG. Think of these filters as the ultimate cleanup crew. They just aggressively scrub away the background noise of everyday life, leaving behind this beautifully clear high-fidelity signal, where a doctor can actually see the crucial P wave, QRS complex, and T waves. Section 3, measuring heart rate and SpO₂. The journey of a heartbeat. So we've talked about the electrical ECG side, but let's see how this builds to capture your pulse and oxygen using just light. It all goes down in a super precise 4-step chronological process. Step 1, the AFE4400 drives specific LEDs to shine light directly into the tissue. This is for photoplethysmography, or PPG for short. Depending on how much oxygen is in your blood, it absorbs different amounts of that light. Step 2, as the unabsorbed light bounces back, a photodiode catches it, and the system amplifies that incredibly faint signal. Step 3. This analog signal is perfectly synced up with ADC sampling to digitize those light waves. And finally, Step 4. Onboard algorithms crunch those numbers to spin out a highly accurate heart rate and SpO₂ percentage. And literally, all of this happens in the blink of an eye. Which leads us to this little number here, plus or minus 2. This single stat anchors the crazy precision of this whole setup. The heart rate calculation has a maximum error margin of just +2 beats per minute, and the blood oxygen is accurate to within +2%. When you're talking about remote medical monitoring, precision is literally everything. This exact level of accuracy is what separates a basic consumer fitness band from a serious clinical tool. Section 4. The mobile app experience, data at your fingertips. Okay, so all this math doesn't mean much if the user can't easily read it. Let's look at the final destination. Those perfectly processed signals are beamed over Bluetooth straight to a cross-platform mobile app. This is where users and doctors get immediate, readable insights. The app gives you real-time, scrolling visual waveforms for both the ECG and the PPG. Right below that, you get these nice, big numerical displays for heart rate and SpO₂. But it's not just a live monitor. The app does continuous data logging and has cloud sync capabilities. So a patient's historical data can be effortlessly shared with their doctor for long-term tracking. So the crucial point here is how the system handles real-world hiccups. Like, what if a sensor just falls off while a patient is fast asleep? Well, under normal operation, you get that smooth, continuous data streaming. But if we enter a lead-off state, an intelligent circuit instantly detects that an electrode has disconnected. It immediately cuts the flow and fires off a mobile alert. This lead-off detection is a massive safety net. It guarantees that no one, neither the patient nor the doctor, is accidentally staring at dead data. Section 5, the future of telemedicine, transforming remote care. We zoomed in on the micro-level engineering. Now let's zoom out and look at the macro impact this is going to have on healthcare. The impact here is really profound. First off, this design actually meets strict international standards, specifically ISE 6061-2-27 for ECG and ISO 8061-2-61 for blood oxygen. Because it hits these heavy-duty clinical benchmarks, and because it runs on such low power, it becomes a true lifeline for elderly patients or anyone managing chronic conditions at home. We're talking about highly cost-effective remote diagnostics. It gives patients peace of mind and totally cuts out those exhausting, constant trips to the hospital just to check basic vitals. And honestly, what we're looking at today is just the starting line. Because the architecture is completely modular, the future upgrades are already mapped out. Pretty soon, we're going to see expansions into simultaneous multi-channel ECGs. We're going to see temperature and respiration sensors added to the mix. And, maybe the most exciting part, this platform is perfectly set up for AI-driven arrhythmia detection, using machine learning to spot dangerous heart rhythms way before a human doctor ever could. I want to read this quote straight from the source material, because it really hits the nail on the head regarding the real-world value here. With further clinical validation and mass production, it has the potential to transform personalized healthcare and remote diagnostics. This isn't just about building a neat gadget for the sake of it. It's about making high-end, highly accurate healthcare accessible to people no matter where they are. And that brings us to a final thought for you to chew on. As this kind of technology scales out of the lab and into our everyday lives, how will continuous remote monitoring change your own future healthcare experiences? Just imagine a world where your doctor actually knows you're getting sick before you even feel the first symptom. That is the incredible power of the AFE4400 and systems just like it. Thank you so much for hanging out with me for this explainer. Keep asking great questions, and I'll catch you next time.